Okay, so in this video, I would like to use Eisenstein's criterion to prove that some polynomials are irreducible over the rational numbers. So these are the polynomials that we're going to prove are irreducible. And the easiest way when you have a polynomial like this, notice all of these polynomials have integer coefficients. And the easiest way to prove that such a polynomial is irreducible is going to be to use this Eisenstein's criterion. So the first thing I want to do is I want to state Eisenstein's criterion. So let's say that you have some polynomial, and we're going to write this polynomial as an x to the n plus an minus 1 x to the n minus 1, and so on. Okay, like this. And we're going to assume that this polynomial has integer coefficients, so I'm going to assume that all of the a0, a1, and so on, all of those coefficients live in z. And then I want to assume that there's some prime number p. Okay, so I'm going to assume that I have a prime number p such that, first of all, p does not divide an. So if you're dealing with a monic polynomial, all of the polynomials that we're dealing with here are monic. So their leading coefficient is just 1. And so if you want to apply Eisenstein's criterion to polynomials like this, you really don't need to worry about this first condition. But in general, with a polynomial, you would have to worry about this. So we assume that p does not divide an. We assume that p does divide all of the other coefficients. So we assume that it divides an minus 1 all the way through a0. And then the last, maybe most important piece is that we want to assume that p squared does not divide a0. So this is a slightly complicated condition. So you want p to divide all of these coefficients. So you want it to divide everything except the leading coefficient. But then you also want p squared to not divide the constant coefficient or the constant term. And the claim is if all of these things are true simultaneously, then this polynomial is irreducible over q, which also implies that it's irreducible over the integers as well. Okay, so how are we going to apply that to our polynomials here? Well, notice this first polynomial, this has appeared in an earlier video that I made, but this polynomial, you can use Eisenstein's criterion with p is equal to 2, right? Because, well, first of all, it's monic, so 2 doesn't divide the leading coefficient. But we also have that 2 divides this coefficient, or this term right here. And then 2 squared does not divide this last term. So by Eisenstein's criterion, we know that this polynomial is irreducible. For the second polynomial, we can do something similar. I noticed that all of the coefficients are, except for the leading one, are divisible by 3. So for this one, I can use Eisenstein's criterion with p is equal to 3, because 3 divides this coefficient, and so on. But if I do 3 squared, 9 does not divide this last coefficient because it is too small. Okay, and so I know that this one is irreducible. So far I have this guy, I have this guy. And then the last one that we need to deal with is this polynomial. This one is going to be slightly more difficult. Make a little bit more space here. Let's come over here. So this last polynomial is going to be slightly more difficult because taking the polynomial as it is, there's no prime number that will work, right? Because all of the coefficients are just 1. However, what I could do is I could try a substitution. And this works when you want to prove that a polynomial is irreducible. If the polynomial as is not in a form that you can apply this criterion, you can make a substitution and try to replace it with a polynomial that that does allow you to apply this instead. So what am I going to get if I do this substitution? X is equal to t plus 1. So I'm going to get t plus 1 squared plus t plus 1 plus 1. And if I expand this out and simplify, I'm going to get t squared plus, what will I have here? I'll have 2t. Well, actually, so I'm going to have 2t, and then I'm going to be adding this t over here. So I'm actually going to have 3t. And then I'm going to have plus 1, plus 1, plus 1, like this. And so now, even though I didn't start with a polynomial where I could apply this criterion, I was able to introduce this substitution, which is technically a homomorphism, which is a different story. And now I get this in a form where I can use Eisenstein's criterion with p is equal to 3. Okay, so that proves that all of these polynomials are irreducible. This last polynomial I will also mention, so this guy right here. So this is an example of what's called a cyclotomic polynomial, which if you're taking abstract algebra, you may have heard about already. But these are the cyclotomic polynomials, so these are usually denoted like phi n of x. And it's actually possible to prove more generally that these cyclotomic polynomials are irreducible in the case where n is a prime. So here what we had was actually the third cyclotomic polynomial. So it's the polynomial whose roots are the third roots of unity, the primitive ones. So this is v3 of x. And you can prove more generally that whenever this number right here is prime, then this polynomial will be irreducible. But yeah, so that proves that all of these polynomials are irreducible, and that's it.